David Fobes. Dr. Fobes received his PhD in physics from Tulane University in 2010, and since 2015 has been at Los Alamos National Laboratory, where he currently is a staff scientist in the Information Systems and Modeling Group. And for the past 2 years, he has worked as a part of the Advanced Network Science Initiative, primarily developing optimization software for various infrastructure networks, including optimal power flow and restoration of electric distribution systems and the hydraulic modeling of natural gas pipelines. And he will present something on PowerModelsDistribution.jl, for which already some advertisement has been made today. And this is an open source framework for exploring distribution power flow formulations. Okay.
Hello, I'm David Fobes from Los Alamos National Laboratory, and today I will be introducing PowerModels Distribution, an open source framework for exploring distribution power flow formulations. Before I get started, I want to introduce the other co-authors and acknowledge our funding sources. PowerModels Distribution and this paper contain significant contribution from Sander Claeys, a PhD student at KU Leuven, Frederik Geth at CSIRO, and Carleton Coffrin, also here at Los Alamos National Lab. This project was funded primarily through the U.S. Department of Energy's Office of Electricity and Office of Energy Efficiency and Renewable Energy as part of the Clean Start DERMS GMLC project. Also by Los Alamos National Laboratory through the LDRD program and by the Center for Nonlinear Studies at Los Alamos. So there's quite a few different motivations for the creation of PowerModels distribution. First, distribution systems have rather unique considerations over transmission systems, making existing transmission-focused software for optimization inadequate. For example, phase unbalance is far more typical in distribution systems, and therefore the positive sequence single-phase approximation commonly used in transmission systems is far less reflective of reality. Also, there's been a remarkable increase in the penetration of distributed energy resources such as solar, wind, and batteries on distribution grids, which when connected back to the transmission system can mitigate the need for traditional transmission network expansion. There are also unique demands of controllable loads such as electric vehicle chargers and HVAC systems. Furthermore, like has happened in the transmission power flow formulation space, there are also an increasing number of approximations and relaxations for unbalanced distribution network optimization problems, and a distinct lack of optimization-focused software that allows for easy comparisons of these different formulations. So what does creating an optimization-first platform for power systems modeling mean in a practical sense? So what requirements do we have? First, separating modeling from the solver algorithms is very important. There exists a number of well-known tools for achieving this kind of abstraction, such as JUMP or GAMS, which result in declarative programming approach, where the program structure is described by the user, but the method for finding the solution is not. In this way, a variety of well-known solvers can be supported to solve a large number of types of mathematical programs, such as nonlinear programming, semi-definite programming, second-order cone programming, or linear programming problems. The direct benefit of this abstraction to optimization problems is that switching between the approaches quickly without having to re-implement equations becomes possible, which is essential for rapid prototyping, that is central to algorithmic research, and it allows for direct comparison of solver performance for identical problems and formulations. Furthermore, to facilitate the development of mathematical programs, modeling layers should be able to enable swift implementations and maintainability. And in particular, especially for multi-phase systems, the modeling layer should include such features as support for vector and matrix equations, automatic derivative computation, and support for semi-definite variables and constraints. So that covers kind of the requirements we need for optimization first approach. But what software out there exists today that covers distribution modeling? There are some very nice full-featured open source software packages that currently exist today for distribution network analysis, but they have a focus on unbalanced power flow algorithms instead of fulfilling the need that we see for an optimization experimental platform. In terms of the recent state of distribution optimization, in practice, the collection of data and construction of mathematical models, a variety of approximations are often made, such as neglecting branch shunt admittance, assuming constant power load models, assuming perfect grounding of the neutral at all buses, or even going as far to assume balanced loads across all phases. And these things are really kind of inadequate for accurately representing distribution systems. A few years ago, PowerModels, a transmission network-focused optimization library, was introduced that followed this pattern of model abstraction. To achieve this, PowerModels is written in Julia and utilizes JMP as the model abstraction layer to decouple the solvers from the problems and formulations. PowerModels also decouples the problem types, like optimal power flow or optimal transmission switching, from the mathematical power flow formulations, including AC polar or second order cone relaxations. Finally, PowerModels was written keeping in mind modern software engineering practices in such a way as to make it easily extensible, which is evidenced by the growing number of extension packages, just a couple of which I list here. And so this is the model that we followed when we created PowerModels Distribution. So in response to the needs for an optimization-focused tool for distribution, and following the example of PowerModels, we built PowerModels Distribution, focused primarily around exploring unbalanced power network optimization problems, such as optimal power flow, OPF with on-load tap changing, and others. As a small side note, we do include a power flow solver, but because it uses the same interface as the optimization problem, it is much more inefficient compared to dedicated power flow algorithms. As with PowerModels, PowerModels Distribution is open source, written in Julia and using JMP. It leverages internal functions and data models established by PowerModels so that we didn't have to reinvent the wheel for every aspect. And where possible, we even reuse some variables and constraints for phase agnostic components. For our data inputs, we have chosen to support the OpenDSS file specification. But it's important to note here that we do not intend to replicate OpenDSS functionality, but only to leverage its mature data format to build network cases and act as a tool that goes alongside OpenDSS that adds to it. Under the hood, in PowerModels, we try to take a generic approach to modeling to avoid edge cases. For example, in the case of branches, the physics of power flow under phase unbalance are described in the framework of Kirchhoff's circuit laws, where equations are linear in current and voltage for fixed impedances. For the coupling of neighboring conductors, the impedance becomes a matrix that includes self-impedance, the diagonals, and mutual impedance, the off-diagonals, where the size of the matrix depends on the context. For example, a Cron-reduced 4-wire network would be 3 by 3, networks with explicit neutral conductors 4 by 4, and we can even see 5 by 5 matrices where earth voltage rises are included. In PowerModels Distribution, the branch model formulations are standardized on multi-conductor pi sections, which support full matrices for both series and shunt elements, and even allow admittance shunts on the from and to sides to be different, which enables gamma sections. In terms of data models for different components, PowerModels Distribution leverages the internal mathematical models of PowerModels for consistency, but distribution components are much more varied and complex than the standard set of transmission components, and therefore in many cases distribution components need to be decomposed into a series of more simple mathematical objects. Here's an example of a flowchart that we use to decompose commonly seen distribution components that you can see in green into mathematical data objects in blue. For a more detailed introduction of the different models of components supported in PowerModels Distribution, either refer to the paper or to the online documentation. One component, though, that I'd like to highlight in particular is multiphase transformers, which can have many different settings in multiphase networks. They can have delta, Y, or zigzag configurations, 2 or more windings, and significant no-load losses, which makes them difficult to model straightforwardly. Therefore, we have included a decomposition model where we break down multiphase transformers, in-winding multiphase transformers into ideal 2-winding lossless transformers and build a loss model from impedance branches to account for the no-load losses. So on this slide, we show an example of a 3-winding transformer with delta configurations and a zigzag configuration that are decomposed down into these ideal transformers and loss model. In terms of the powerful formulations already included in PowerModels distribution, we have a nice set of formulations that include several nonlinear formulations, semi-definite and second-order cone relaxations, and several linear approximations, as you can see here in this table. These formulations cover several different categories, but the bus injection model and the branch flow model, multiple variable spaces, such as current voltage and power voltage, and multiple coordinate spaces, like polar or rectangular coordinates. We've also strived to make sure the user experience for PowerModels distribution is as simple as can be expected for an optimization-focused tool. Here I show a simple workflow for installing the package, loading a data file, defining an optimization solver, in this case the open source IPOps solver, and running an optimal power flow using an AC polar formulation. And you can see you get your results out here, and it's all very straightforward. On the right, I show how we define an OPF problem to illustrate how easy it is to define your own problem specification, where you can basically compose your problem specification by looking at adding different variables and adding constraints in a straightforward fashion and adding an objective at the end. In order to validate our mathematical models, we performed comparisons of the AC power flow between PowerModels distribution and OpenDSS on several IEEE test cases. And we showed that the voltage deltas across these networks so that the comparison between the OpenDSS values and our voltage values on each bus, we show those voltages differences to be small, less than 1E7 for each of the cases, as you can see in this table, in this central table here. We also perform some comparisons of several of the formulations on a selection of the IEEE cases, demonstrating the performance of the different formulations in context. So here we show a comparison between AC polar and AC rectangular. You can see the results of the objective results are the same across those two formulations. We also compare SDP and SOC formulations, and you can see the time performance and the gap percentages of each of those for the different test cases. And refer back to the paper for a more detailed discussion. As for the future of PowerModels distribution, development is still very active. We recently released a new version that contains a data model abstraction that introduces a user-facing model that more closely matches engineering realities of the system and pushes the decomposition I discussed to a lower layer. We are now actively working on adding support for explicit representations of neutral and ground conductors, which will entail directly modeling 1- and 2-phase components, and we will be adding that in our next major version. We have also had requests from the user community for many different features, including harmonics analysis, short circuit calculations, and problem-specific solvers. So in conclusion, we have developed a free open source toolchain for the optimization of distribution network power flows, which complements existing tools by providing an optimization-first approach. We have demonstrated using PowerFlow the validity of our physical models on a variety of unbalanced IEEE test feeders, and we have included a robust OpenDSS parser written natively in Julia to ingest distribution test case data. And as a final point, I just want to mention that we think that our work here has highlighted dire need for a library of unbalanced OPF benchmark cases similar to the PGlib ACOPF benchmarks. Thank you for your attention.
Okay, thank you very much, David, for this presentation. We have a few questions. We have questions from panelists and the Q&A. The first to ask the question was Patrick Panciatici, and his question is also a feature request. Did you implement node breaker models for reconfiguration? Is a complex and important problem?
Yeah, so we do have a switch model that's native to PowerModels distribution right now. We don't have a problem implemented yet, an optimization problem implemented in PowerModels distribution, although we have built ones for custom projects internal at Los Alamos. So it's probably, you know, in the kind of shortish term that we would add more features that focus on switches, because yes, I agree, definitely reconfiguration is a very complex and important problem that we are actively researching, but we don't have a definitive version yet that we wanted to raise up to PowerModels distribution. Okay, thank you. Then from an anonymous attendee, have you compared the computational time of different QCP and SOCP solvers? Can you recommend the best one for this specific problem? So unfortunately, I haven't done that. We haven't done that at Los Alamos. The SOC problems were added specifically by Frederik Geth and Sander Claeys, and they are the ones who've done the most research on them. I think actually Frederik gave a nice talk yesterday morning in one of the early morning sessions, and I would recommend checking that talk out. He covers the relaxations and the performance of different ones. So I don't have a specific solver that I would recommend necessarily based off of my research. Okay. And then, so let me have a look. Then another question, which is a question from Brian Palmentier. And it's a question that actually also was my question if nobody would ask a question. How do you manage the constantly evolving Julia environment with no guarantee of backward compatibility, and in the same way also the different versions of PowerModels distribution might have slightly different internal organization or data models? How likely are things written here now to work long-term without modification? And given that the current version is 0 point, I have an expectation about that, let me put it like that. So maybe you can comment on that. Yeah, Julia is actually, I would say, much more stable than in the past. They've hit the version 1 now, and we are fully backwards compatible from version 1.0 up through the current version. We have continuous integration set up, so we're constantly testing. In terms of breaking changes, we follow the semantic versioning system. So anytime you get a major release, you know, you can expect that there might be some breaking changes. That being said, we try to minimize breaking changes as much as possible where it makes sense. In terms of like using the typical user interface where you're just applying a formulation that's already in PowerModels and running a problem definition that's already in PowerModels, you shouldn't have any major problems. We try to keep those as stable as possible at all times. If you are writing your own optimization problems using like a mixture of your own functions and some of our variables and constraints, there could be breaking changes in the future, obviously. We do try to, we've been kind of on a big kick of renaming constraints and variables so that they're much more intuitive what those constraints and variables are based off of their name. Although we hope that that will become stable in version 10. And then, so yeah, so things might break there, but we're also very careful to document any name changes that we make. Like I said, we follow standard industry software engineering practices. So when we make those breaking changes, we document them in pull requests and in the documentation in the changelog.
Okay, so is there an intention to have, let's say, a stable industrial version and an R&D version, which is maybe a little bit more vibrant? And
so I would say any of the point releases that we make, like any release that we make that has like an actual version that you can get directly from the Julia package repository is stable. If you're looking for development stuff, master is where it's at. We do try to keep breaking changes out of master and put them only in like release candidate branches. So we try to keep things as stable as possible for people. But because of the versioning system that Julia has, you can definitely pin to a version and it will always work for you.
Okay, that I think is a very complete answer to this question. I have a comment here from Carleton on one of the earlier questions. Carleton was also involved in many of these publications is that the Mosaic seems to be the best solver for conic problems, IP-opt for nonlinear problems, and Gurobi for QP and LP problems. And I think from Marta's presentation earlier, we saw very similar outcomes. So that was a question, an answer to the question earlier.
He also brought up that version 10 is likely to be close to whatever version 1.0 is going to look like, and that's correct. Version 10 represents like one of the biggest additions we're going to make with the explicit neutral, and that should be like a feature complete enough that we can release a version 1 of the software, which will indicate that it's going to be pretty stable as long as you're on version 1. And then if we make any major breaking changes, which we wouldn't expect to happen very often necessarily, it would go to version 2 and so on.
Okay, thank you very much.